Okay, so I think we can get started. Hello, everyone. Welcome to the SNAPP seminar series. So first, let me just briefly go over the instructions in case you missed them. So please mute yourself during the talk because we only have this one broadcast channel here. However, you are encouraged to turn on your video so the speaker can see some feedback, and we can also get that like seminar in a conference room kind of a nice feeling to it. So if you have any questions during the talk, you can post them in the chat box, or you can wait until the question break or like the Q&A session at the end to ask the speaker directly. And the talk video will be recorded and it will be posted publicly. So if you do not wish to appear in the video, you can mute yourself on Zoom or just watch the YouTube live. And the slides are also on the SNAPP website. Okay, so I'm going to start recording right now. Just give me a few. Record. Okay, so today we are really glad to have Srikant as our speaker. And Srikant is the co-director of the C3.ai Digital Transformation Institute and the Frederick and Elizabeth Nearing Professor in the Department of ECE and the Coordinated Science Lab at the University of Illinois at Urbana-Champaign. Srikant has received numerous awards. I'm going to just name a few here. He is the recipient of the 2015 Infocom Achievement Award and the 2019 IEEE Koji Kobayashi Computers and Communications Award, and the recipient of several Best Paper Awards, including 2015 Infocom Best Paper Award, 2017 Applied Probability Society Best Application Award. He's the editor-in-chief of the IEEE and ACM Transactions of Networking from 2013 to 2017. And his research interests are very broad, as far as I know. His research interests include applied probability, machine learning, and communication networks. And today he's going to talk to us about load balancing in bipartite graphs. So everyone, let's welcome Srikant.
Thank you, Wayna, and the other organizers for inviting me to give this talk. As Wayna mentioned, I'm going to be talking about load balancing in bipartite graphs. So this is joint work with Wenta Wang, who is going to be a senior at Tsinghua University, and Xingyu Zhao, who recently completed his PhD at Ohio State and is currently working at Alibaba and will be joining Wayne State University as a professor in January. So this talk is about data centers and cloud computing. I think most of you know what these terms are, and data centers and cloud computing is used by every major company that we can think of, including Amazon and Google and Microsoft and Dropbox and everything. So sort of a defining feature, one can call it that, is that a data center is large. So you have large numbers of servers, a large network, massive amounts of data. And as we have seen, even in the applied probabilities and sigmetrics communities over the last several years, this size has actually motivated a number of our queuing theory type of problems. So what does the size being large mean? So from a queuing theoretic or applied probability perspective, that means you have a large number of servers. So when a job arrives, so you can enqueue the job in any one of these servers or begin service immediately if a server is available. And of course, the gold standard for this kind of routing is join the shortest queue. So one tries to emulate join the shortest queue in some manner or other. But the challenge is that the number of servers is large. And so the question is, how can you extract minimal information from the network to perform your routing in an efficient manner? So I think we are all familiar with power of D choices, join the idle queue, batch filling, many other algorithms. So all of these are motivated by the fact that the data center consists of a large number of servers. And so the key question is, when a job arrives, where should you, which server should you assign it to? Okay. However, that's a classical problem, in my opinion. That's a traditional problem. So in practice, actually, you don't have that much choice. So it's not like a job can be routed to any server that you want. The data, so typically you require some data to execute your job. For example, you can type in presidential election in quotes along with CNN. So this will try, Google will try to search and find the number of occurrences of the term presidential election, or all the stories involving presidential election in CNN. And of course, this data is not stored in every single Google server. Obviously, it cannot be stored in every single Google server. This is just simply too much. And so what you would do is store the data, spread it out across servers. Then you might replicate the data on multiple servers, both for the purposes of load balancing as well as for reliability reasons. So if a server goes down, then the data is available elsewhere. Okay. A different type of instance is also machine learning models. So when I've talked to people in the industry, so Amazon, for example, when you query it, for example, something like, let's say, iPhone 10R or something like that, then it'll show you all the iPhone 10 models, the used ones, the new ones, the cases associated with it, chargers for it, headsets for it, and so on. And so the way that it does it is it routes your query to an appropriate machine learning program or a machine learning model that resides in one of the servers or a few of the servers. And those servers will process your query and display what you want. So again, even though Amazon might have like thousands or millions of servers, in fact, your query is not, your choice is not amongst all of them. So it's choices or a limited set of them. And so sort of what I call modern load balancing or load balancing with locality looks more like this. So a job that's sent to a server can only be served by servers which with the data or the machine learning model that the job needs to execute. So in this example, let me pull up a pointer here. Okay, so here's a job. So I've colored it green, and here are two servers. So this server has the green data, and this server also has the green data. So it's the data associated that's needed to execute this job. So when this job arrives, this job can be sent to this server or to this server to execute. It cannot be sent to this server because this server does not have the data available, okay, to execute the job. Similarly, when this server, for example, receives a job which requires the yellow data, it cannot send it arbitrarily to anywhere in the network. It can only send it to this server. So I put an X here to denote that this green job, for example, cannot be routed along, and it cannot be routed to this server because it does not have the green data. Okay. So I think this type of data locality, to the best of my knowledge, was one of the first papers, and possibly the first mathematical paper dealing with it, was from Weina's thesis, which was advised by Lei Ying. And so it is this paper, Wang, Zhu, Ying, Tan, and Zhang, who looked at data locality for the first time, at least to the best of my knowledge. But their model is slightly different in the sense that what they allow is data migration. So in their model, suppose you have a green job that arrives here, it can be sent to this server, except that if the job is processed at this server, it might take, for example, twice as long compared to processing at one of these two servers. Okay, and this model was further developed and looked at more extensively by Xiaomin Xie and Yi Lu. I think Yi talked about it, Lu talked about it at the Stochastic Networks meeting in San Diego. Okay, so in the model, what's different about the model I'm considering here is that I'm not allowing data migration. So when a job arrives, you can either send it to this green job can be sent to the top server or the bottom server, but it's not allowed to go to this server. Okay, so that's the difference between these original models of data locality and the one that I'm considering today. So probably the primary motivation for our work is this beautiful paper by Devankar, Sem, and Johan on routing in networks, job resource allocation in networks. So they don't specifically look at it, the level of detail that I mentioned in the previous page, but in their model, jobs arrive to nodes, and you have an underlying graph with some connectivity. And when a job arrives at a node, it can be sent to one of its neighboring nodes. Okay, and under the usual Poisson arrival exponential service time assumptions, what they showed was this system behaves very much like join the shortest queue. Okay, so even under some constraints on the connectivity of the graph. So in other words, if the graph is sufficiently well connected, but the sufficiently well connected requirements actually, only imposes a very sparse connectivity constraint. It doesn't really require the graph to be fully connected or even close to that. But basically, what they show is that the system behaves very much like a JSQ system. What they proved was stronger than what I'm going to say here, but I'm going to sort of simplify it and mention one thing here. So essentially, if you look at, this is a standard definition that many of you may be familiar with. So if you think of SIT as the fraction of servers with queue length at least I, what they show, so S1 of T therefore is the number of busy servers in the network. So the number of busy servers in the network, I guess I think the arrival rates here are all lambda. So this is not, this is different. I mean, I have, I think I've called it lambda 1, lambda 2, lambda 3 here, which is in our model, but I think in their model, if I remember it correctly, I think it should all be equal lambda. So the fraction of, so the total arrival rate is n lambda. And so the fraction of servers that are busy in steady state goes to lambda, and the fraction of servers with more than two or more jobs waiting goes to 0 when the size of the system becomes large. And this implies, of course, 0 waiting time. So jobs get processed as soon as they arrive for all practical purposes. Of course, this is not true for finite n, but in the limit as n goes to infinity, this is basically what they showed. So this was our primary motivation, this paper, and sort of starts to get a little bit at data locality in the manner that I mentioned in the last page, in the last slide. So the main difference is that I guess here it's assumed that every job that arrives at a particular server or generated by the server, for example, the data for that job is contained in all the neighboring nodes determined by this graph structure. Okay, so this may or may not be true, but this is a very nice paper which sort of points out that you can sort of maybe handle data locality. So I guess the next natural extension to think about is what if you have different types of, so if you're going back to this paper by Mukherjee, Borst, and Lewardin, so you can think of jobs arriving at a node as being of just one type, meaning that they all require the same data, okay, or machine learning model. But what if there are multiple types of jobs that arrive at a server? So some jobs may require one type of data, some jobs may require a different type of data. So for example, to this node, you can have a green job arriving, in which case it can be routed to the top server or the bottom server. So maybe this server itself does not have the green data available. So in which case it'll try to route it to one of these two. But if this router also, or this server also has the green data that you need, then it can either choose to keep it here or to route it to one of these two other servers. But if you have another type of job that arrives, which is yellow here, so it requires a yellow type of data, then you cannot route it along these two paths, right? So because you cannot route it to these two servers. I mean, forget about paths. You cannot route it to these two servers because these two servers do not have the yellow data that the job requires to execute. So what you would do is you try to find a server that has the yellow type of data, and then you route it. So this is the only server in this picture that has the yellow type of data, and so you will have to route it here. Okay. So if you think about it in terms of the graph that was in the in Debancourt et al.'s paper, you can think of the graph as being multiple graphs, one for each color of data that you have. So you could have a connectivity that is described by there could be yellow edges, which sort of point out where the yellow servers are, and you can route it along those edges. Or you could have green edges, which tell you where the green jobs have to be routed, and so on. Okay, and potentially each of these types of jobs can have different arrival rates. So that's another deviation from the model that I described in the previous slide. So instead of thinking about it as a graph, it actually turns out to be more general to think about it as a bipartite graph, which seems a little bit silly, because here you have a general graph and here I'm talking about a bipartite graph, which is a special structure. But essentially, the idea is that you can take this graph. So suppose you have two types of jobs arriving at this node and one type of job arriving at this node, and these servers tell you what type of data that they have. You can think of it as a bipartite graph. So you can think of replicate this node as two nodes on the left. Okay, so I have these three nodes, which I'm drawing on the right, and associated with each arrival type, I have a node on the left. So basically, this is saying that what it's saying is that lambda 11, which corresponds to the arrival rate of green jobs at this node, can be thought of as a left node, which is generating jobs for these two servers. And so this node and this node together are generating jobs for this server, which has the yellow type of data. Okay, so in fact, it turns out the bipartite graph is a more general model. So this was a model that was considered by Cruz, Jonquière, and Schneer. So where they said that there are L types of servers on the left, and then N types of, so I can call it, let's just to distinguish the left and the right, let me call these ports and these servers. So the L ports on the left and N servers on the right. So these L ports, or the L nodes on the L left nodes, generate jobs for the right nodes. Okay, and then there is a connectivity between the left and the right, which determines which job can go where. So the whole point is that jobs don't need to be generated at servers, or you don't need to even think about jobs as being generated at servers. They can just come from anywhere. The main point is that jobs have to be routed to the appropriate servers, which are on the right. So jobs are generated somewhere, and just for conceptual simplicity, we sort of denote the L types of jobs as L nodes on the left. So this is essentially the L job types here, the N servers, and there's a connectivity from left to right, which tells you which servers can serve which type of jobs. Okay, so they assume Poisson arrivals of rate lambda L. So of course these don't have to be the same. This is not homogeneous arrival rates, and the service times or the service rates need not be homogeneous either. And they considered the join the shortest queue discipline and showed that the system is stable. So they didn't consider performance, they just looked at stability. And they showed that the system is stable if and only if this graph viewed as a network can support a maximum flow equal to the total arrival rate. So what does that mean? So basically think of an imaginary source node on the left and an imaginary destination node on the right, and take the source node and connect it to all these left-hand side nodes. Basically, since these are essentially edges talking about connectivity, they don't have any capacity constraints. You can imagine these edges as having capacity of infinity. And then you have a destination node. And what they showed is that if this single source, single destination network flow problem admits a maximum flow that is equal to summation I lambda I, then the system will be stable. Of course, I mean, you need mu1 plus, this should be slightly larger than lambda I for stability in a stochastic sense. But essentially, if the maximum flow can be supported in this network, then you have stability. So they showed that join the shortest queue in this more general model of the Debancourt's paper is stable under join the shortest queue. So what we are interested in is more than stability. So is JSQ optimal in this model in the sense of minimizing mean response time? And what is the mean response time when the system size does not scale to infinity? So we're interested in two questions. One is, in the limit as n goes to infinity, do you have optimal response time? And it turns out that join the shortest queue itself may not be optimal for this problem, but a slight modification is optimal. And but we are also interested in getting bounds on the deviation from the mean field limit for finite size systems. So for finite n, we are interested in knowing what the delay will be. Okay. So our main results are the following. So what we show is that JSQ is asymptotically provides zero delays in the case of homogeneous servers. So if you assume the mu's are all equal, then JSU provides asymptotically zero delays. And join the fastest of the shortest queues is asymptotically optimal for heterogeneous servers. So what do you mean by join the fastest of the shortest queues? So in JSQ, you join the queue which has the the job arrives. You look at all the servers to which you can send the job, and then you join the shortest of the queue. You join the server with the shortest queue. In JFSQ, what you do is you break ties in favor of, so if you have two queues which have the equal queue length amongst all the shortest queues, there are multiple queues with the shortest queue length, then you would break ties in favor of the fastest amongst them. So if there are only two queues, for example, one with service rate 2 and one with service rate 1, then you would send the job to the top queue. Of course, one should remember that JFSQ does not really need to know the processing rate of each server. You only need to know which server has, which server is faster than the other. So you don't actually need to know the exact service rates, but you just need to send it to the server which is the fastest. Which typically you can know this information is available. But you may not know the exact service rate, but you'll have some idea of which server is faster and which server is slower and so on. So we also, in addition to proving these two results, we also provide a delay bound for finite size systems. So that's the rest of the talk. And at this point, I want to mention that, I guess much to my surprise and probably much to Dibankar's surprise, when we sent this abstract in for this talk, Dibankar realized that he had been working on something similar. And so he had been working on showing that JSQ has asymptotically zero delays in the case of homogeneous servers for this bipartite graph model. It's Ratan and Mukherjee, so they are working on it. Our paper is also not posted anywhere yet, so we're hoping to put it up on archive in a few days. And I guess they're also planning to do that. And so the first box that I said here is very closely related to the work of Ratan and Mukherjee. But I think their techniques and their results, while similar in spirit, are somewhat different. I guess they use process level convergence. And as you will see, I use what I call the drift method, which is also called, I guess, the basic adjoint relationship. So that's my favorite technique for proving things. And that's what I do. That's what we do in this paper. Whereas Dibankar and Ratan use process level convergence and show different things in the paper. So I haven't looked at their draft of the paper carefully enough to compare the conditions. So we need, of course, just like in the original paper by Mukherjee, Borst, and Leeuwarden, there's a condition on the connectivity required in the graph, and we require something like that. And Ratan and Mukherjee also have some condition, although they call it a compatibility condition. But I haven't compared the two models to see whether the conditions agree or are different or whatever. So Dibankar, do you want to say a few words? Is my characterization correct?
Yeah, I think you covered most of it. It's like the model is kind of similar, but we look at homogeneous arrival rates, and we also consider power of D-type policies compared to.
That's right. Yeah. So they also cover consider power of D choices rather than just join the shortest queue. So in this talk, mostly I'll talk about join the shortest queue and join the fastest of the shortest queues. But actually, all the proofs go through unchanged for join the idle queue and join the fastest of the idle queues. So I think that is whereas Ratan and Mukherjee consider power of D choices. Okay. So I will talk about the simpler case first of homogeneous servers. I'll primarily focus on that because the proof gets more notationally complicated, and there are multiple sort of state space collapses that one has to prove for the heterogeneous server case. So I'll primarily talk about the simpler case and just give you an idea towards the end about what one needs to do to extend it to the more general case of heterogeneous servers and join the fastest of the shortest queue. So I'll confine my talk today to JSQ and homogeneous servers because contains most of the big ideas without getting into the somewhat complicated stuff that one needs to do to study JFSQ. Okay, so in our model, we assume a finite buffer size, B, but the buffer typically scales with n. But our results are sort of so we wanted to get a bound on the delay for fixed B, fixed number of servers, and yeah, so that's, I guess those are the two things. And so for that reason, we consider fixed buffer sizes, because in practice buffer sizes are fixed as well, and it helps with the mathematics because a lot of the issues such as, you don't have to worry about the existence of the stationary distribution and so on. It's much easier, but it gets at the many of the main results much more easily with this assumption. So we're going to assume finite buffer size B, and we're going to assume that the total, so going back to the bipartite graph models, I have L different arrival rates here, and I'm assuming homogeneous servers. As I mentioned, it generalizes. So I'm going to assume that the arrival rate is n lambda, where n lambda is some number between 0 and 1. And we are interested in the large server limit and in performance guarantees for large but finite size systems. We're interested in what happens in the limit as n goes to infinity, but we're also interested in finite size systems. Okay, so we need an assumption, which is sort of the equivalent of the Mukherjee-Borsellin condition. So what we need is that if you take any subset of the servers that is sufficiently large as a function of n, then the sum of the arrival rates of ports, not the left-hand side nodes, which we call ports, that are not connected to n, must be bounded by some d tilde times n. So for example, if you consider these two servers, of course, this is not a large fraction of n, but just for illustration purposes, if I consider S to be this set 1 and 2, then ports 2 through L are not connected to 1 and 2. So if this were a large fraction of the number of servers, then I would make sure, then the assumption is that the total arrival rate here is bounded by d tilde times n. Okay, so the number of jobs, or the arrival rates of jobs that cannot be served by the set of servers cannot be too large. Okay, and of course, if you consider the nodes 2 through n, of course, all the ports on the left are connected to 2 through n, so this condition is easily satisfied. So our main result is this. So it has a lot of notation. So essentially, let's just focus on this. So what is this? This is the total number of jobs in the system. So SI is the fraction of jobs, a fraction of servers with greater than or equal to I jobs. So if I add it all up, that's the total number of jobs in the system. So ignoring epsilon for the moment, I mean, of course, we cannot ignore it because here it's divided by epsilon. But basically, what we're interested in is that we want to show that the total number of jobs in the system is close to lambda. Okay, so this will essentially mean 0 waiting time in the queues. What we show is that it actually is close to lambda plus epsilon in the expected sense, and the bound is like order b square over epsilon n, where if you recall, b is the buffer size, n is the number of servers in the system. So as n goes to infinity, this quantity might be it will go to 0. Of course, since we are assuming a finite buffer system, we also need to argue that in this case, the blocking probability also goes to 0, which actually it will. Okay, so let me take a more simpler example. Suppose I make the buffer size log n. The buffer size can be anything. The d tilde. I mean, there are some constraints on the buffer size. It should be something like order n. For this, no, it cannot be larger than order n. Yeah, that's our assumption. And so if b is log n and d tilde is, for example, epsilon over 2 log n, then you can show that this expected value goes to 0 and the blocking probability goes to 0 as n goes to infinity. So let's see what the time is. So it's roughly half an hour. It's almost 11 o'clock. So maybe this is a time to pause and see if there are any questions. I guess there were some questions in the chat box.
Yeah, Srikant, maybe I can.
Hi, Shane. Yeah.
Hey. Yeah, thanks. So I was just thinking about this policy of looking amongst those queues that are shortest, and then the fastest of those. And just thinking about how that relates to the case where you have maybe one queue that is slightly longer, but it corresponds to a server that's super fast. And somehow I sort of feel like that second option would probably get that job served a little sooner. Is it the case that in the limiting regime that you're considering, you do have a sort of an air gap? So in the limit, essentially no jobs wait, and therefore you do that?
Yeah, no jobs wait. And then what happens is that the system, but additionally, to minimize the response time, you also need to make sure that the faster servers are filled first, and then the second fastest servers are filled second, and so on. So that's what makes the proof a bit more complicated there. But that's basically what's happening.
Great, thank you.
Yeah. So there's Sushil Verma has raised hand.
Yeah. This well-connected graph condition seems interesting. Is there any relation of this with the Hall's condition?
In the marriage theorem you're talking about?
Yeah, marriage theorem, but then let's say there's weights as well, which are the rival rates, and then the Hall's condition considering the weights as well.
I haven't thought about it. That's a good question. So maybe I can show you the next slide. I don't know if I have it in the next slide. So here, I guess what I was imagining it more along the lines of random graphs. The reason is that you can't really control how. I mean, it's very difficult to precisely put the data in the servers to achieve the connectedness condition. So you would expect, people to put data. As time progresses, more and more servers are being added to the network, and then more and more data is being added to the network, and so there is probably some sort of randomness in the way this connectivity works. And what I'm thinking here is that in a random graph, is this condition satisfied, which is sort of what in the Mukherjee et al. Paper they did. And so we have some idea here which says that if the graph is fully connected, you would need NL edges, whereas it's sufficient to have N plus L divided by 1 minus epsilon times d to the edges. So I haven't really thought about it in a deterministic fashion, although the condition is like that there. But I think what is really important here is that whether a random graph satisfies this condition or a random assignment of data satisfies this condition. It is an interesting question. Maybe a different way to think about your question is that, is there some way that I can place the data so that this condition is satisfied? And I don't know if that's related to Hall's condition or not. Maybe that's probably an interesting thing to think about if we haven't thought about it. Yeah, I think Veena had a paper, if I'm not mistaken, Veena and Lei, on how to place data along with routing, right? Is that correct, Veena?
We assume a static placement of the data. We didn't control the data placement.
Oh, okay, you didn't do that. Okay.
So there's another work with applications in manufacturing. So they're like plants, and then plants can be flexible, and then how much flexible the plant should be to manufacture the product so that you're minimizing the delay.
Oh, okay. Interesting.
And there they introduce this condition as a complete resource pooling condition.
Oh, okay. Whose paper is this?
Sorry, I don't remember.
Okay.
Yuanzhang is one of the co-authors.
Okay.
It's basically heavy traffic regime viewpoint of a similar problem, and there one needs complete resource pooling condition, and that's related to the Hall's condition.
Okay. I see. That's where Sushil is asking this question. I see.
I have a quick question, Srikant. So I'm trying to understand the role of B in your theorem. So the bound on the number of non-empty queues deteriorates with B. The blocking probability also deteriorates, and it looks like even D tilde deteriorates, or
D tilde is, it's a complicated relationship. What I'm saying is it's probably easier to think about it this way. So B is log n. It doesn't deteriorate because as n becomes large, it doesn't. Okay, I see. For fixed n, I think you need some flexibility. I think B tilde provides some flexibility in putting things there. I mean, if you just have like one buffer, for example, in each queue, then yeah, I guess primarily the reason we did this was when I later talk about resource pooling, we needed a B. I mean, it's okay. The best answer to your question is we haven't thought a lot about how to optimize this. We haven't thought more about what is the best choice of B tilde. Can we make B tilde small or large? But this is interesting. So what you're saying is that how does I've been mostly thinking about it in terms of whether this is going to 0 as a function of n. So you're asking why does it? No, but wait a minute. D. So here D is like 1 over B2. It's kind of a complicated relationship here.
So I'm asking, why would I not pick B equal to 1? Like, which aspect of the theorem will deteriorate by will actually benefit from a larger B, right? It looks like.
Let's see. Okay, so let me see. So if B tilde is 1, so B is 1, then you would require D tilde to be n. So the connectivity should be dense, right? That's not good.
So that well-connected graph assumption, as I'm reading it, like the larger the D tilde, the condition becomes easier to satisfy, no?
So the sum of arrival rates not connect. That's true. So let me think. So the sum of arrival rates to ports not connected with S. So we want to make sure that the arrival rates to ports not connected to S should be sufficiently large. But does that? So what I'm confused about is that does that mean? I would think that that is easier to satisfy. That is true. But is that necessary? Is that necessarily a good thing? So, Fernando, are you saying something?
Yeah, the blocking probability gets worse. Huh?
Yeah, but he's saying that B here also is actually getting is getting better here. But here, if D is large here, this part becomes large. Yeah, so it's a complicated interplay. So let's see. So if B is 1, so basically then D is large. That means that this part will become large.
Yeah. Okay, got it.
Yeah. Good. Thanks, Fernando. Yeah, right. Yeah. So that's why I find it hard to think about it actually in this manner. So it's easier to take some examples to think about it.
Right.
Yeah. Any other questions?
So Gail also has a question on the related to the graph. Do you want to still ask or?
No, David wrote something I can live with.
Okay.
Okay. Okay. Then.
Okay, then I'll continue. Okay, so I guess this is all obvious. So the response time, I guess, at least in this, so if we take an example for B tilde and D tilde, and for B and D tilde and so on, you can see that the response time is close to 1. But we can also give bounds for finite time. So it is bounded by the mean response time is 1 plus epsilon over a lambda plus order, something that goes to 0. Okay. So I think we've also discussed this. So I'll skip this slide as well. So basically, the idea is to show that, so even though we have a bipartite graph, essentially the system behaves very similar to a single server queue where the total arrival rates are pooled and the service rates and the resources are pooled. Okay, so it behaves like a single server queue, and the waiting time goes to 0 because of this reason. So this is what we want to show, and this is the basic idea behind the proof. Okay, so in particular, in classical load balancing, we join the shortest queue. As I mentioned earlier, the fraction of busy servers will go to lambda, and the fraction of servers with greater than or equal to 2 jobs goes to 0. And we want to show something similar for bipartite load balancing as well. So my favorite way to study all of these problems is what I call the drift method, which is also called the basic adjoint relationship. It's something that we have developed over the years with Attila Arielmas and Sivateja and Vaina and a number of other people. So just to quickly review what the drift method is in the case of heavy traffic and why it does not work in this case and what we need to do for this case. So let me just remind people how we do things in heavy traffic. So in heavy traffic, what we do is that we try to identify a lower dimensional space S in which the queues live. For example, in join the shortest queue, all the queues have equal size, roughly in heavy traffic. So that means that the system lives in a one-dimensional space, okay? And what we do is then you try to come up with a Lyapunov function or some function. Here, the function that we typically use is the projection of Q onto this subspace S, and then you show that and then you use the fact that the drift of the norm square of this projected Q length does not change with time. So if you look at time t and time t plus dt, mostly in the past, except in the paper with Vaina, we primarily worked with discrete time. But in continuous time, you just look at a small interval of time dt, and then you set this drift to be equal to 0. And this gives bounds on the norm of Q length, or so here I'm using the true norm, but what you are really interested in is the total sum of the Q length. But we can show that this really, essentially, since we are not using the norm of Q squared, but rather the norm of the projection of Q onto this subspace, if we show that the projection of Q onto the orthogonal component of Q, if that is small, then essentially this is like looking at the Q length, but we are throwing away all the unnecessary parts that interfere with our analysis, and that's basically how we get bounds on the expected total Q length. But the key component here is to show that the expected value of the perpendicular component is small, and to show that that is small, so you look at the drift of the perpendicular component, the norm of the perpendicular component. And then it is well known that if the Lyapunov function satisfies some condition and the Lyapunov function has a negative drift, then you can get bounds on the moments of the Lyapunov function in steady state. And this is a classical result due to Hayek from 1982. But these days we mostly use the result by Bert-Seamus, Gamarnik, and Tsitsiklis from 2001, which gives more refined bounds so we can get tighter results. But basically, these two are related papers, which essentially show that a drift condition implies something about moments in steady state. Okay. The key extension of this type of ideas to the large server limit. So our paper can be thought of as a network extension of the work of Liu and Ying from 2018. So for one thing, we are no longer interested in total queue length. We want to show that the queue length is actually close to 0. I mean, the only jobs in the servers, nothing is waiting. So the cost function that we'll use is a different cost function. So, but it's well known that if you use HFQ as a cost function that you're trying to minimize, then the integral of HFQ serves as a natural Lyapunov function. The key difficulty is that the drift of this Lyapunov function is hard to analyze. So what you do is that you analyze the drift of a simpler system and show that the generator of the system that you're studying and the generator of the system, the approximate system, are close to each other. I guess this is so I'm citing Liu and Ying here because that's the closest to our paper, but that Liu and Ying paper itself is sort of motivated by an earlier paper by Lei Ying on using Stein's method. Stein's method uses this idea of trying to compare the generator of the simpler system to the generator of the true system. And Lei's paper in turn, of course, was influenced by the papers by Gurvich, Stolyar, and Jim Dye and Anton Braverman on Stein's method. And so this is really closely related to Stein's method, but the reason I'm not really calling it Stein's method is that Stein's equation is trivial to solve in my case. And so essentially, I'm just simply using the fact that the generator of the true system is close to the generator of the simpler system, which is basically the idea in all of those papers. Dye, Braverman, Stolyar, Gurvich, and Ying, and now Liu and Ying. And in heavy traffic, so the second difficulty is that in heavy traffic, we exploit the fact that the state lives in a lower dimensional space. So this is very useful in analyzing this drift. So there is no direct analog. So there isn't a state space collapse in the sense that you think about it in heavy traffic, but there is something similar. So what Liu and Ying exploit is the fact that when the number of jobs in the system is large, then the number of servers used must also be large. Okay, so there is resource pooling happening here. So you cannot have a large number of jobs in a small number of queues and a whole bunch of queues that are being empty. Okay, this cannot happen. So this is basically what Liu and Ying exploit in essentially in a manner. So they construct a very clever Lyapunov function, which is not this that I've used that I mentioned here, but rather a different Lyapunov function, and show that its drift is negative, and then use the result by Bertsema, Skamarnik, and Tsitsiklis to prove the result. So basically what we are showing in this paper is that these ideas also work in the case of a network, and more importantly, in the case of join the fastest of the idle queues, or the join the fastest of the shortest queues, you have to actually do a lot more work. You have to do multiple state space collapses, which I'm not going to talk about here. So I don't know whether to call it, it's not quite state space collapse, it's not multidimensional state space collapse in the sense of heavy traffic limits, but it's somewhat similar. So you have state space collapse happening in multiple dimensions, and or resource pooling happening in multiple dimensions, and we use the ideas in this paper to prove our result. So let's move along, and so let me give you an outline of the proof in the remaining time. So basically, we are interested in this as the Lyapunov function. So the Lyapunov function is the total number of jobs in the system must be close to lambda. And so therefore, this is not the Lyapunov function. This is the metric of interest. And so the Lyapunov function is just simply the integral of this. Okay. And as I mentioned earlier, you try to take this Lyapunov function and set its drift equal to 0 in steady state, or more precisely, you apply the generator of the Markov process to this G, and then use the fact that that is equal to 0. But this turns out to be hard to manipulate directly, and this is where the Stein's method or the generator coupling idea turns out to be useful. So in the paper by Liu and Ying, what they show is that they consider only parallel servers, but they're interested in power of D choices, and the question is that what should D be to get 0 delay? And since you're trying to get 0 delay, so the intuition is that you're trying to get close to join the shortest queue, or actually a single server queue. So this parallel server system in their case, and in my case, this complicated bipartite graph actually looks very similar to a fluid queue with arrival rate 1 minus delta and 1. So normally you would expect 1 minus delta to be lambda, so the arrival rate is lambda, departure rate is 1. But because the system is not truly MM1Q, you sort of make an allowance for it and say that it may not be exactly lambda. We don't know what it is. So, but we're going to assume that it's 1 minus delta. And if you choose delta cleverly, the whole proof works out. So that's basically the idea. So what does this generator coupling mean in analytical terms? So you set the expected value of the generator equal to 0. And what you do is that if the generator is a differential equation, then this generator applied to G will be G prime multiplied by the dynamics of the single server fluid queue, which basically decreases at rate minus delta. So I want to show that this generator applied to G looks very similar to the second term here. And so how do I do it? By adding and subtracting this term, right? By adding and subtracting this term, I've not changed anything. So I have G of G minus H of, so G prime is what the metric of interest. Remember, we got the Lyapunov function by integrating the metric of interest. So this is H of S times minus delta minus H of S times delta. And now I'll take this term to the left. So this gives me the answer that I want. I'm interested in the expected value of H. So this is the expected value of some constant times H. And I'm interested in showing that this is small. And if you look at this equation, this is exactly the same as showing this generator behaves like the fluid system. So this is the basic idea behind Stein's method, which is essentially the same as roughly similar to the drift method, except the clever thing that they do in Stein's method or the generator coupling idea is to couple the generator to a much simpler system and show that this difference is actually small. So the generators of the true system and the approximate ODE are close, then the performance metric of interest is small. Okay, so this is the basic idea. So if you expand the right-hand side, there are lots of complicated terms on the right-hand side, but it turns out that most of them are very, very easy to bound. There's only one term that remains that sort of requires some work. And that term is just this part. So basically it says that, so there's an indicator function, which basically it says that whenever the total number of jobs in the system is large, okay, where I'm not defined all of these terms here, and for the purpose of this talk, that's not relevant. So when the number of jobs in the system is large, okay, so I'm interested, the term looks like the metric of interest multiplied by lambda plus delta minus S1, okay? So what does this mean? What we need to show is that if this condition is satisfied, this indicator function is not 0. So if the number of jobs in the system is large, we need to show that the number of busy servers is large. If S1 is larger than lambda plus delta, then this whole quantity will be negative, and so I can just upper bound it by 0, and then it basically get rid of this term. So remember, we are trying to get an upper bound on this term. So if you have a term like this, to get rid of it, you upper bound it by 0. It turns out that you can't really upper bound it by 0. You can show that it's actually a very, very small quantity. And I'm going to give you some intuition as to what that small quantity is. So this is what I mean by state space collapse and resource pooling here. So essentially what this is saying is that you don't want the system to look like this. When there are lots of jobs waiting in the system, you don't want a large number of empty servers, idle servers. So you want the system to behave like this, okay? So what this is saying is that if sum of SI is large, then you should have enough number of busy servers so this quantity becomes negative, or negative with high probability, or not negative with a small probability, and so therefore this upper bound will be small. So how do you prove this? So another way to pictorially think about it is that if the number of waiting jobs in the system, so here I'm summing up from I equal to 2 to be SI. If the number of waiting jobs in the system is large, we want the number of idle servers to be small, okay? So this gives the intuition for this is a slightly modified version of the Lyapunov function that is used in the Liu and Ying paper. And so the key intuition there is what I showed in this picture. So you want to show that if this is large, then this is small. And this is basically what is captured in this Lyapunov function. So this Lyapunov function has one term, which is the total number of waiting jobs in the system. The other term is basically S1 needs to be close to lambda. This is what's captured in this term. Which is so if you think about it, if V is small, okay. So if V is small, if this quantity, if you can prove that this quantity is small, you have to have one of two things will happen. Either the number of jobs in the system is small, or the number of servers, because the minimum has to be small, so one of them has to be small, okay? So how do you show this? So I want to, in the remaining few minutes, I just want to make the connection between this and the well-connectedness condition, and that just sort of essentially completes the proof. So if this Lyapunov function is large, okay, since this is the minimum, both of these quantities must be large, right? So if the second of these quantities is large, it simply means that the number of idle servers is sufficiently large, okay? And let me go to the next slide. If the number of idle servers is large, the assumption before was if the number of idle servers is large, we want the total arrival rate into the idle servers to be, I mean, that was the well-connectedness condition. So if you're considering any subset which is sufficiently large, then the arrival rate into that subset will also be large, so that the number of idle servers will start decreasing very, very quickly. Okay, so this is basically the idea. Then you can use the papers by Hayek or Bertsima Tsitsiklis and Bertsimas Gamanik and Tsitsiklis to show that in steady state, this Lyapunov function that we're interested in is small. So I'm not going to go through all those details. I mean, those are a lot of work, but which Wentao did, but the main point is that I guess there should be a plus here. The main point is that putting it all together, you can show that the metric of interest is of the order of b squared divided by epsilon n. So the key ideas, I just want to summarize the key ideas. So the key ideas are network extension of the generator coupling and resource pooling, and using network connectivity in the manner that I showed in the previous page. So this is where the network connectivity condition becomes important. But this procedure becomes more complicated, but it can be done for drawing the fastest of the shortest queues, where one has to demonstrate resource pooling twice. So okay, well, I won't get into it, but basically, so this similar ideas work for drawing the fastest of the shorter queues, but you have to sort of use this Lyapunov function and the Hayek / Bertsimas Gamanik Tsitsiklis type of results multiple times to get the result. So let me briefly talk about the JFSQ result. let me see how much time I have, just 5 minutes. So when faced with many idle servers, join the shortest queue chooses one at random, whereas to join the fastest of the shortest queues, basically you break ties in favor of the fastest servers. And the approach is similar and more involved. But let's say when you have heterogeneous servers, let's say you're interested in minimizing the total queue length. What would you do? So there are M types of servers here. So I'm calling the service rates mu1 through mu capital M. And I'm going to say alpha 1 fraction of them are of type 1, alpha 2 fraction of them are type 2, and alpha m fraction of them are type m. And so to minimize the total queue length, I just need to minimize this quantity. This is just the total queue length divided by n. And of course, you have to have the flow conservation constraints, which basically say that the network should be able to handle your load. So this is the stability condition. So the total amount of service that you provide should be equal to the total arrival rate. Okay. So if you solve this optimization problem, it is quite obvious that you want this to be small. So what you want to do is that you want to set, so you basically want all the fast servers to be full, and then the second fastest servers to be full, till all of them that you can fill up till, and then there'll be one set of servers which you may not be able to fill because the arrival rate is slightly less than 1. Okay, so this is the optimal solution to this simple linear program. And this is precisely what JFSQ does. So if the arrival rate is 8 and there are servers with rates 3, 3, 2, 2, and 1, basically it'll try to fill these 3 servers first. Of course, I mean, not when you have exactly 1 server, 2 servers of this type. Imagine there are 200 servers like this and 200 servers like this. What it'll do is that it'll try to fill up the fast servers first, and then it'll fill up the remaining ones of the second fastest server. And therefore, it'll solve this optimization problem exactly. So that's basically what one has to show in the case of join the fastest queue. And you'll have similar connectivity conditions. Maybe I'll skip the slide. Basically, it is roughly similar to the condition where with the homogeneous servers, but to achieve optimality and everything that we have to have a slightly stronger condition for some pools of servers and slightly weaker condition, or roughly the same condition that I had before for other pools of servers. But those are details. So let me wrap it up. So basically, we've studied bipartite load balancing. We showed that join the shortest queue is optimal for homogeneous servers, asymptotically 0 delays, and with the delay bound for finite servers. But we also showed that join the fastest of the shortest queues is optimal more generally. I mean, I should say near optimal, because it's all true only in the limit as n goes to infinity. For finite n, we have bounds. So one might argue that join the fastest of the shortest queues might be still difficult to implement in practice. So of course, one can use JFIQ. So everything that I said goes through for JFIQ, join the fastest of the idle queues. So you just only look at the idle queues and then join one of them, or if there are no idle queues, just route randomly. And the results, I assume that lambda is fixed, but you can also extend it to the case to sub-half-infinite regimes. So Vaina also mentioned that one should try to suggest an open problem. I'm sort of reluctant to call this an open problem because we haven't thought a lot about this, but let me just say that this is not something we have attempted. It's not at least an obvious extension, or maybe it's obvious, but we haven't thought a lot about it. So the one big assumption we are making is that when jobs arrive to the left, we assume that all the servers here have the same service rates independent of the job type. Okay, so more generally, of course, you can think that red jobs have are smaller than green jobs than yellow jobs and so on. So the service rate could be could be class dependent. Okay, so if the service rates are class dependent or job class dependent, then I'm not sure that what we have done immediately extends at least. So our assumption is that mu I1 equal to mu I2 is equal to mu IL, and so maybe quote unquote open problem is what if this assumption does not hold? So this is something interesting that we'll probably think about next, and other people are welcome to think about it too. So that's it. Thank you.
Okay, thank you, Srikant. Let's thank Srikant for the great talk. Okay, so now is the Q&A session. I'm going to ask you a quick clarification question first. So So all the analysis for the JSQ is not for heavy traffic, right? It's just for a fixed lambda, a constant lambda, and in the large server regime here, is it?
I mean, for us, lambda, B, and things like that, nothing is really scaled. So, but what we can show is that when do you get zero delays in our problem? And what we are able to prove is that you can get zero delays even if lambda scales as 1 minus 1 over square root of n.
Okay, but it covers.
But there is nothing about heavy traffic or anything like that in the analysis. Yeah.
Okay, even the state space collapse result.
There is no, yeah. That's why I sort of didn't want to call it state space collapse. It's not exactly in that state space collapse in the heavy traffic sense, but essentially what it's somehow you have to use the fact that when the number of jobs in the system is large, the number of servers used is also large. So that's, if you call that state space collapse, that's what I mean. Yeah, that's basically, that was in the Liu and Ying paper.
Mm-hmm. And also like for the optimality of JFSQ, that's also for the large, is for the same kind of regime, right? Like lambda.
Well, I mean, again, we have bounds for every n, but in the limit as n goes to 0, it basically solves this optimization problem that I mentioned.
Right.
Yeah. So in the limit as n goes to 0, it solves this optimization problem. But for finite n, of course, we have bounds on how far it is, what the total queue length is.
Okay. Yeah.
So we can show that it's close to the smallest queue length possible. But when it's close in the sense that we can bound the deviation. Yeah.
I see. Okay, thank you. So I think Lei has his hand up.
Hey, Srikant, this is Lei.
Lei.
So for the connectivity condition, is that condition also necessary, or if not, like how close is that to a necessary condition?
Good question. I don't have an answer to that. I mean, that basically makes all the math work out. Whether it is necessary or not, it's not something that we have thought a whole lot about. Yeah. What does it mean for it to be necessary? I guess one could ask the question, when does this expected value of the metric of interest not go to 0, right? I guess that may be one way to think about it. And then you can say, if this condition is not satisfied, can you show that this does not go to 0? We haven't thought about it.
Right.
I
so
don't,
like
I don't
where
know.
there's a counterexample such
Right,
that the condition
exactly. Yeah,
value.
yeah. Good. So Ventao, I don't know if you've thought about this. Have you? I mean, I don't know if Ventao's still on the line. Are you there, Ventao? Ventao is in China, and sometimes the connectivity is.
Yeah, he replied in the chat.
Yeah,
he
that is. Yeah.
What did he say?
Yeah, he said that we did not consider it because we think the lower bound is much more difficult.
Yeah. So yeah, we haven't done that part yet. That's a good question. So that could be another open problem here.
Okay, thanks.
But I have a question. I have an answer to Wena's question. So basically, we have some basic results on the heavy traffic region. So basically, the fixed number of servers and lambda goes to 1. So we have some preliminary results on the heavy traffic region, and also we have some results in the many server heavy traffic region, but we didn't cover it in this paper.
Right. Yeah. So I see. I didn't realize that was. So I thought she was asking about this particular thing. Yes, we can prove some things in heavy traffic, but there the methodology is closer to more the standard. The state space collapse methodology that I mentioned earlier. So here I wanted to focus on this other thing, which I thought was not as well known, this idea of Liu and Ying. But yes, so you can use either Stein's method more directly or the drift method to prove heavy traffic optimality as well. Yes.
I see. Okay. I think Siva Fija wants to ask a question.
Hi, Srikant. Can you go to slide 30? So my question also relates to Veena's question. I'm trying to kind of find the connection between the heavy traffic state space collapse and the notion here. So here you have this picture, right? So there is this red line, and then you want to say that it's not possible for some queues to be very much above this red line. if there are some queues that are very much below this red line. And this red line happens to be at 1 here because the average queue length is between 0 and 1 for this regime, because this is the mean field regime, or because this is like lambda equal to 1 minus square 1 over square root of n regime. But in heavy traffic, what happens is this red line will be much higher, because that is classical heavy traffic. So
you're talking about where n is fixed and you're letting lambda go to 1.
Yes.
Okay.
So what I want to say is that in that regime, if I give you a queue length vector, then think of the average queue length and then draw a red line there. And then I want to say that you can't have queues too far either on either sides of this red line. And that is one way of thinking about the queue perp result in
right. Yeah.
So this is a more refined way of characterizing that state space collapse in some sense. There we just look at Q perp, but
here fundamentally you don't have this lambda going to 1. So there basically Q perp is small compared to Q when lambda goes to 1.
Right.
Here there is no such thing. Here just simply what it is saying is that since you're doing join the shortest queue or join the fastest of the shortest queue or join the fastest of the idle queue. So or join the idle queue, for example, even. Essentially what it's saying is that if the number of jobs in the system is large, since you would have basically tried to put them in the idle queues first, this kind of situation is unlikely to happen, basically.
Okay, so think of the regime where lambda is like 1 minus epsilon. And this epsilon is also dependent on n, like n power minus alpha. So you mentioned these results are applicable.
Yeah. You can do it. Yeah, right.
Yeah. So what I'm trying to say is, so the classical heavy traffic regime is alpha equal to infinity. So what I'm trying to say is there we use the Q perp state space collapse. Right. Here you use this notion. I think there is like a continuum between these two.
Okay. I see. Maybe Lei has thought about this. I mean, I don't know if Lei has some comment on this.
Yeah, I think it's not as precise as the traditional heavy traffic state-space collapse, where you can define a proper subspace, which is like makes sense. You can explain what that subspace is. Here, you collapse to some subspaces. It's not like as well defined as in the traditional heavy traffic sense.
Yeah, exactly.
I think
that's
it's
why I wanted
to state space collapse than the
right. Yeah. So I put state space collapse in quotes sometimes because I don't know what to call this, but it's sort of like that. It has, but you're right. I mean, there might be some continuum, but it is a bit different though. So it's not clear to me.
Yeah. So I think maybe follow up with Sivasija's comments. Here you have this red line, but you have also large deviations from the red line in terms of queue length, and deviate by length by 2 by 3. But when you move up the red line, then all the queues kind of concentrate around the red line, and the deviation also becomes small. That's more traditional state.
Right. Exactly. So here we really need to show that for this. I mean, you can also see that there is no norm involved here. So I don't know. It's a bit different, but yeah, there is some connection. I don't know how to say beyond that. But at least in terms of the Lyapunov function and the drift, and the techniques are very similar. But I can't visually imagine it in the same way as one visually imagines heavy traffic state space collapse. But there could be some connection. Maybe Sivateja has some ways to think about it that I'm not able to think at this point.
Okay, thanks. Maybe I mean I have some more thoughts, but maybe I can do that offline because I don't want to hog up the question.
Sure. Yeah. Are there any other questions?
Yeah, I have a question. I want to ask what happens if lambda is not known or lambda itself is time varying?
I don't know about time varying lambda, but we don't require lambda to be known. The algorithm doesn't require lambda to be known, but of course the conditions require lambda to be known. I mean,
sure.
Conditions are in terms of lambda, not that it's required to be known. But basically, you need the system to have sufficient connectivity, and sufficient might be a function of lambda, but we don't need to know lambda for the algorithm. Is that your question, or?
I mean that does answer part of the question, but you're saying if the lambda itself is time varying, as long as it satisfies the condition.
Time varying is I don't know. Yeah, that's something that generally we don't consider. I mean, maybe the way to think about it is that at least in data centers, the volumes are so large that things reach steady state. So you can even think about the system as, maybe during morning time or during daytime, and the load on the servers is large, it's one system, and at off-peak hours it's another system, and you can look at each of them separately rather than thinking about a time varying lambda.
Okay.
So usually I just think of lambda as a constant. Yeah. Anything else? Okay, Wayne, it looks like.
Yeah, so if there are no further questions, I'm going to end the formal part of the seminar right now. And let's thank Srikant again for the great talk.
Thank you.
So next week, I'm going to make a quick announcement. So for next week, we are going to have Andrea Montanari speak, and he will be talking about the self-induced regularization from linear regression to neural networks. Okay, so if people want to hang around a little bit, you're welcome to do so. I'm going to just end the recording and the live streaming right now. Okay.